Smart contract vulnerabilities represent critical security flaws that threaten blockchain applications. These exploits occur when attackers identify and leverage bugs in contract code to steal funds, manipulate data, or disrupt operations. Understanding these common attack vectors is essential for building secure decentralized applications. Throughout this lesson, we'll explore the most devastating vulnerabilities, including reentrancy attacks, integer overflow issues, access control failures, and learn proven strategies to prevent them. A reentrancy attack is one of the most dangerous vulnerabilities in smart contracts. It occurs when an attacker repeatedly calls a vulnerable function before the previous execution completes, effectively draining the contract's funds. Here's how it works. First, the attacker calls the withdrawal function in the victim contract. The victim contract sends funds to the attacker before updating its internal balance state. During this transfer, the attacker's fallback function automatically triggers and recursively calls the withdraw function again. This malicious loop continues until the contract is completely drained. The infamous DAO hack of 2016, which resulted in the loss of $60 million worth of Ether, was caused by this exact vulnerability. Let's examine a vulnerable withdraw function. In this insecure implementation, the function first retrieves the user's balance amount. It then sends Ether to the caller using the call function with the balance value. Finally, it sets the user's balance to 0. The critical problem here is the order of operations. The contract sends funds before updating the state variable. This creates a window of vulnerability where the balance still shows the original amount even after funds are sent. An attacker can exploit this timing gap by having their contract's fallback function call withdraw again and again, draining all available funds before the balance is ever set to 0. The solution follows a pattern called checks, effects, interactions. In this secure implementation, we first verify that the amount is greater than 0 using a require statement. The crucial difference is that we update the state immediately, setting the user's balance to 0 before making any external calls. Only after the state is safely updated do we transfer the funds using the call function. By resetting the balance first, any attempt at a reentrant call will fail because the balance is already 0. This simple reordering of operations completely eliminates the reentrancy vulnerability and protects the contract from recursive exploitation. Integer overflow and underflow vulnerabilities occur when arithmetic operations exceed the boundaries of what a variable can hold. An overflow happens when you add to a variable and it exceeds its maximum capacity, causing it to wrap around to 0. For example, if you have an unsigned 8-bit integer at its maximum value of 255, adding 1 causes it to overflow back to 0. Underflow is the opposite. Subtracting from 0 causes the value to wrap around to the maximum. For an unsigned 8-bit integer, 0 minus 1 becomes 255. Attackers can exploit these vulnerabilities to manipulate balances, bypass restrictions, or create tokens out of thin air. Fortunately, Solidity version 0.8 and later provides built-in protection against overflow and underflow. The compiler automatically checks all arithmetic operations and reverts the transaction if an overflow or underflow would occur. In this safe add function, the simple addition operation is protected automatically. If adding A and B would exceed the maximum value for unsigned 256-bit integers, the transaction reverts instead of wrapping around. For contracts using older Solidity versions before 0.8, developers must use the SafeMath library, which provides protected arithmetic functions. The add function from SafeMath ensures safe addition by checking for overflow before performing the operation. Access control vulnerabilities occur when authorization checks are missing or improperly implemented, allowing unauthorized users to execute privileged functions. These are among the most common and easily exploitable vulnerabilities. There are several typical scenarios. Functions lack proper modifier protections, making critical operations accessible to anyone. Developers incorrectly use transaction origin instead of message sender for authentication, which can be exploited through phishing attacks. Functions may have default public visibility when they should be restricted to internal or private access. Initialization functions might be left unprotected, allowing attackers to claim ownership of deployed contracts. Each of these mistakes can lead to complete contract takeover and fund theft. Proper access control requires explicit authorization checks using modifiers. First, store the owner's address in a state variable. Then create a modifier called onlyOwnerThatChecks if message sender equals the owner address. If not, it reverts with a not authorized error message. The underscore symbol indicates where the function body will execute. Apply this modifier to sensitive functions like withdraw by adding onlyOwner after the visibility keyword. Now only the owner can execute this function. Always use message sender for authentication, never transaction origin. Message sender represents the immediate caller, while transaction origin always refers to the original external account, which can be exploited if that account is tricked into calling a malicious contract. Unchecked external calls represent another critical vulnerability. When contracts make external calls to send Ether or interact with other contracts, these calls can fail for various reasons. The recipient might reject the payment, gas might run out, or the target contract might not exist. If the calling contract doesn't verify the return value, failures occur silently without reverting the transaction. In the vulnerable example, the call function is invoked, but its return value is ignored. The contract assumes the transfer succeeded and continues execution. In the secure version, we capture the success boolean and immediately require it to be true. This ensures that if the external call fails for any reason, the entire transaction reverts, preventing inconsistent state and protecting contract integrity. Let's review essential security best practices. First, always follow the checks affects interactions pattern. Validate all inputs and conditions first, update your contract state second, and only then make external calls. This ordering prevents reentrancy and ensures state consistency. Second, use reentrancy guard mechanisms, which implement mutex locks to prevent functions from being called recursively. Third, conduct professional security audits before deploying contracts to mainnet. Expert auditors can identify subtle vulnerabilities that automated tools miss. Finally, test extensively using unit tests to verify individual function behavior, integration tests to check component interactions, and fuzzing to discover edge cases with random inputs. Remember, smart contract code is immutable once deployed, so security must be built in from the start, not added later.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.